is the story of a most remarkable achievement in modern American railroad construction. Of how the men of Morrison-Knudsen Company moved mountains of earth and rock to build a dry land causeway across the briny width of Utah's Great Salt Lake for the Southern Pacific Railroad. The largest steel barges of their kind ever made were used for the job of building the broad base for the big fill straight across the trackless middle of the lake. Skilled nautical engineers used a perfectly aligned system of targets and depth measuring devices. Theirs was the task of directing the big barges into position for dumping at pre-designated locations to keep the great submarine embankment rising evenly toward the surface. The old railroad line, forced to bypass the lake far to the north, is rich in historic lore. In 1869, when two smoke-spouting locomotives bumped cowcatchers at Promontory, a roaring chapter in the annals of American railroading was closed. The first transcontinental line was completed, and its finale celebrated by driving the famous Golden Spike near this point. In 1904, the famous Lucin Cutoff was completed, and SP trains were routed directly over the lake for the first time in a series of causeway sections and a long wooden trestle. 44 difficult miles were hereby trimmed from the main line right-of-way. The new route traveled for a distance across the southern tip of Promontory Peninsula, protruding down from the north. The original plan was to span the lake entirely with an earth and rock dike. However, the early embankment builders were only able to consolidate fill sections 7 miles from the eastern shore to Promontory Point, 2.5 miles into the lake from here, and about 5 miles eastward from the west shore. The remaining gap of open water was spanned by a wooden trestle supported by huge timber pilings. This crossing, more than 12.5 miles long, served the SP faithfully for more than half a century. However, for years, this single-track span with its low speed limitations had kept operations to a snail's pace over this vulnerable stretch of rail. The SP badly needed a more stalwart crossing to keep pace with the demands of an age of jet propulsion and fast diesel-powered locomotion. After years of planning for a solid landfill over the lake, SP finally decided to place the new causeway parallel to the old trestle some 1,500 feet north. MK was awarded a $49 million contract for the job in March 1956. It was one of the greatest earth-moving challenges in American construction history. The actual planning stage was begun in 1953 when SP, in cooperation with the International Engineering Company, a principal MK subsidiary, began making test samplings of lake bottom materials to determine the most favorable route across the lake. The lake bottom along some 6 miles of the most feasible line of crossing was composed of a deep, mush-like layer of soft mud, intermixed with the skeletal remains of thousands of generations of saltwater shrimp, the only form of animal life in the lake. Soil engineers called this substance organic clay. Laboratory tests and calculations were made to determine how much lake bottom material would have to be removed by deep water dredging to develop a sufficiently solid foundation for the massive embankment. Hence, the relatively new science of soil mechanics played an important role in the ahead-of-schedule creation of a great stable fill across the lake. A stalwart, rock-ribbed right-of-way that would allow SP trains to travel at maximum dry land speeds over the new span. By early spring 1957, after an extensive holing-in period at the site, the causeway operation was well underway. Huge dredges sucked out millions of tons of lake bottom mud, allowing the big bottom dump barges to release their massive cargoes to create the broad, underwater portion of the causeway. Shallow draft flat-top barges were used to bring the embankment up above water level. Bulldozing rigs pushed their rugged cargoes over the side, raising the dike an average of 3 feet above the surface of the lake. large fleet of fast-moving diesel end dump trucks working around the clock from both ends of the fill added vast quantities of gravel and rock to the embankment after it had been raised above the surface. The rugged spine of rock extended further and further into the lake. Fill material flowed into the causeway at the fabulous rate of more than 3.5 million tons a month during peak production. On numerous individual days, placement exceeded 150,000 tons, somewhat of a record for causeway construction. Solid mountains of rock on each side of the lake were honeycombed with tunnels. Tunnels to be packed tight with high explosives for producing some of the biggest non-atomic blasts ever set off by man. Nearly 10 million pounds of powder were used during the course of the job. Seven days a week, around the clock, the job of loading and placing fill material into the growing embankment continued. Barges, side dump rail cars, and a fleet of some 60 massive Euclid trucks loaded by large electric shovels turned the peaceful Salt Lake setting into a roaring theater of unending production. The excavation, loading, barging, and placement of the vast quantities of gravel used in the causeway provided a spectacular show all of its own. Gravel was hauled principally in bottom dump barges, each carrying the equivalent of a train of 70 heavily loaded railroad dump cars. In the Little Valley Barrow Pit, electric shovels loaded out a never-ending succession of long bottom dump trucks. These massive machines, hauling some 50 tons, delivered their cargoes to a steel unloading bridge at the head end of the job's elaborate conveyor system. A heavy jaw crusher below the dumping point reduced any rock to a maximum size of 8 inches to prevent damage to the broad, fast-moving rubber belt that transported the gravel to the barge loading dock 2 miles away. This high-speed system was specially built to handle gravel at the prodigious rate of up to 90,000 tons a day. The gravel was stockpiled over 2 massive steel reclaiming tunnels from which a pair of 6-foot wide belts carried the material to fill the giant bottom dump barges. The twin loaders, handling some 12,000 tons an hour, could completely load a barge in 15 minutes. From each side of the lake, the above-water portions of the new crossing were extending further and further toward the center. Trucks were rolling up a combined total of some 20,000 miles per day, and individual round-trip hauls were approaching 20 miles in length. As the rugged stretch of rock above the surface of the lake was lengthened, MK's mariners in hard hats operating the massive push-tow barges, which, with their powerful twin-engine tugboats, made up perhaps the world's largest landlocked construction navy, continued to ply the super-salty, super-buoyant water of the lake. At Lakeside on the west shore, the causeway was anchored at the end of the old 5-mile-long fill. Here, near the old trestle abutment, MK heavy equipment operators built a broad, delta-like dumping ground. A railroad spur was extended out into the lake on a temporary fill. Rock for use in the causeway embankment, pushing out from the west side of the lake, was delivered by railway cars to the dumping ground from a mountain quarry some 3 miles away. Here, the rock was reloaded on Euclid end dump trucks by power shovels and an overhead loading rig. From the reloading area, the trucks hauled the material to the end of the lengthening west portion of the embankment for placement where barging operations had brought the fill above the water surface. Operations centered at Little Valley near the other end of the causeway, however, provided the really big show of production. Here was located the barge harbor, the major rock quarries, the amazing $2 million gravel conveyor system, and the bustling new construction town of Little Valley itself. At the start of the job in 1956, the building of the town, warehouses, homes, a supermarket, dormitories, schools, and shops, was carried out with the same speed and precision that characterized establishment of important beachhead installations during World War II. Within a matter of days after award of the contract, whole trainloads of materials began to arrive. The first of approximately $20 million worth of equipment and job installation supplies were procured to put the big undertaking in operation. Three massive dredges were soon at work, excavating the elaborate barge harbor and a 250-foot wide channel leading out to the deep water of the lake. Thousands of long, sturdy wooden piles were driven deeply into the soft mud of the lake shore to stabilize foundations for heavy-duty loading docks, a marine railway, and other important installations. Two stiff-legged derricks were erected for rock loading operations. The 6 mammoth steel bottom dump barges used on the job were railroaded to Little Valley in sections from Napa, California, and welded together at the edge of the harbor. The 5 smaller flat-top barges prefabricated at Provo, Utah, were also assembled at the Little Valley shipyard, as it was called. Colorful launching rites were staged on completion of the first big barge, a ceremony attended by SP and MK officials and Utah business leaders. Miss Utah of 1956 christened the vessel with real champagne as it rolled down to the harbor on the wheeled carriages of the new marine railway. Deep-water dredges led the way across the lake as the job settled into a truly gargantuan routine in early 1957. Dredges whose long cutting heads were capable of reaching downward nearly 90 feet. They worked like giant vacuum cleaners in cutting out a foundation trench in the lake bottom clay, in some places as deep as 55 feet. During the job, they moved nearly 20 million tons. Then came the great bottom dump barges. These tremendous workhorses of this landlocked Navy were ingeniously designed and constructed to haul their mighty loads in some of the heaviest water on Earth. Each was almost as large as a football gridiron. The tugboats as well were built especially to operate in the extremely heavy water. Experienced tug skippers from Pacific Coast and Gulf ports found this new assignment different in many ways from ocean harbor work. The brine of the lake contains 7 times as much salt as seawater, and navigation, especially during stormy weather, was extremely difficult. Consequently, every phase of the job was pushed ahead relentlessly during periods of easy navigation. As dumping continued, engineers made constant fathometer recordings of the underwater embankment profile. From fathometer tapes, office technicians created cross-section drawings to show the contour of the developing fill across the lake. These were used by positioning engineers to direct the barge dumping on the submarine embankment. A mother barge near the end of the underwater fill was the rendezvous point for the flat-top barges, whose cargoes brought the dike above the surface of the lake. This stationary ship bearing bulldozing equipment was known as the Mayflower. The broad, buoyant, flat-top vessels drawing a scant 10 feet of water were maneuvered alongside the mother craft directly above the underwater fill placed by bottom dump barges. bulldozers were placed aboard the two ends of each incoming barge down heavy wooden ramps. The dozers, scraping and squealing across the steel decks with seeming nonchalance of the hazards of going overboard, quickly unloaded the giant cargoes into the briny water of the lake. Along the ridge of rock left in the wake of the flat-top barge operations, an endless parade of dump trucks continued, raising the fill to its full height of 12 feet above the water. A heavy protective outer layer of supersized rock was added to prevent storm damage to the sides of the causeway. Thus, with big machines and by ingenious engineering methods, the men behind this great combination land and marine undertaking were writing a new saga of Western railroading at its colossal best. Rock and gravel were being shipped to sea 24 hours a day. 600 MK men, exercising their skills and operating some of the most spectacular equipment on earth, were moving a mountain into a briny inland sea for modern railroad progress. By mid-1958, with nearly 50 million tons of fill materials already placed, the job was pushing further and further ahead of a rigorous time schedule. At the main gravel and rock quarries, seldom less than 135,000 tons of material was being moved by the mammoth electric shovels and big trucks on any normal day. When conditions were ideal, production totals exceeded 160,000 tons moved into the growing embankment during 3 8-hour shifts, day after day. Excavation, drilling, and mucking crews worked steadily, creating a continually enlarging maze of underground tunnels, undermining mountains of solid rock with an elaborate system of so-called coyote holes, into which were placed the gigantic stores of high explosives for the great blasts for which the job was noted. For days ahead of each of the larger blasts, powder was transported into the network of 5 by 7 foot tunnels by rail cars and conveyor systems. Day and night, loading crews continued stuffing the great underground system with seemingly endless quantities of high-powered explosives. 50-pound cartridges of high-test dynamite were used as priming charges for the big explosions created largely by massive amounts of ammonium nitrate. On January 5th, 1958, MK crews completed loading for one of the largest non-atomic blasts in history. 2,138,000 pounds of concentrated force was ready for detonation. This was the greatest of all the giant Salt Lake blasts. The big shot produced a big muck pile, nearly 5.5 million tons of well-broken rock. Enough to keep the shovels, trucks, and barges busy for months building the elaborate new causeway. The use of steel skips and stiff-leg derricks was planned as a means of slipping the heavy rock easily into the empty bottoms of the barges to prevent damage to the dumping gates. However, to keep truck unloading progressing steadily, the skips were used almost continually. Other trucks dumped directly into the partially filled barge compartments. The flat-top vessels, maneuvered under a bridge-like dumping platform at the south end of the harbor, were loaded by an endless succession of fast-moving trucks whose rugged cargoes were spilled down a heavy chute onto the broad deck of the barge. By such vigorous production, work was pushed steadily ahead on the gigantic task of closing the long open water gap across the lake. For 2 generations, SP trains on the heavily traveled overland route from Chicago to San Francisco had been forced to cruise at greatly reduced speeds across the trestle. Progress demanded a safe, foolproof crossing over the stretch to end an ancient bottleneck. The new causeway, with its solid makeup of gravel and rock, would allow trains to travel at full operating speeds over the fill. It would withstand indefinitely the destructive forces of storm, fire, or sabotage. An interesting sidelight to the far-flung project was in the field of radio communications. More than 70 two-way radios were used as the vital link in coordinating the work of the huge spread of land and sea equipment. All floating gear, main offices, and some 30 cars driven by job supervisors were in constant touch with 2 central radio stations. By late spring 1959, all barging work had been completed, and fill operations were confined to trucking materials to raise the big causeway to its maximum height. Although meager in size at its crest, the great bulk of the fill is below water. Its broadest base sections exceed 600 feet in width, and its height exceeds 90 feet in some places. 2 concrete culverts for boat passage and to equalize the level of the lake on each side of the fill were built on dry land at Little Valley, floated into place, then sunk at their permanent locations. The great job was nearing completion. Meanwhile, vessels of the big construction armada drowsed sleepily at dockside in Little Valley Harbor. After 3.5 hectic years of dynamic production, a strange silence and tranquility seemed to prevail over the site. Spreads of heavy equipment scattered all along the length of the embankment dressed down the top surface, preparing the grade for early track laying work. Engineering groups made careful and continuous cross-section studies, checking the full width of the surface portion of the fill every 100 feet, and also making measurements to determine the rate of settlement along the great new right-of-way. Other men with fathometers mounted in rowboats made exacting surveys of the broad underwater portions of the embankment, also checking every 100 feet crosswise of the berm or submarine shoulder of the fill to determine that the embankment was built to full section width. These readings, taken regularly, were carefully checked against previous records to ascertain the definite stability of the fill at all points. At the same time, telephone line crews were winding up work on a new wood pole communication system across the fill. Excavating for and setting the poles in an orderly manner along the heavy rock ridge of the embankment was an engineering achievement in its own right. In addition to Southern Pacific's special telephone lines, a large composite cable was strung to regulate automatic railway signal and switching devices over the route. Crews of engineers continued to check the internal water pressure of lake bottom clays underlying the causeway to ascertain its rate of consolidation. Pre-installed steel pipes enclosing the intricate pressure measuring equipment were extended downward below the fill from platforms set at various points on both sides of the causeway. On July 9, 1959, a full 9 months ahead of schedule, the big crossing was completed by MK forces. The last of nearly 65 million tons of material was in place, and another epical chapter in the history of American railroad construction came to a close. It was an achievement to be chronicled alongside the joining of the rails from east to west in 1869 and the driving of the celebrated Golden Spike. No pageantry or fanfare attended completion of the fill. The nearest thing to a spike driving ceremony was the mere tacking down of centerline markers by MK engineers to help line the path for the steel rails. Rails already being strung by SP's men and machines along the smoothly surfaced crest line of the new crossing. The line itself was being extended rapidly westward from the Little Valley end of the fill by SP's top-hand track-laying experts. Modern rock ballasting equipment followed closely as work was pushed to divert the heavy traffic over the new causeway at the earliest possible moment. An ingenious mechanical tamping machine jammed the ballast down firmly between the ties. Work pushed ahead rapidly. 30 days after track work was begun, the new crossing was ready for use. This tremendous achievement is symbolic of the magnitude of Southern Pacific's whole region-wide comprehensive program of construction and improvement that is helping to build this railroad's golden empire of the West and the great Southwest into one of the most abundant and flourishing sections of the United States. The Southern Pacific Company has always been known as a pioneer in research and technological development. It has constantly expanded a whole host of allied services that continue to benefit more and more the millions of people and widely diversified industries of the vast region covered by its spreading network of steel rails. This magnificent $50 million dry land crossing of Great Salt Lake is a monumental tribute to the spirit of American industrial progress at its finest. A solid symbol of the ruggedly individualistic character of the men who have made the Southern Pacific Railroad one of the nation's truly great industrial enterprises.